SME has a rich history of supporting manufacturing. That led technology pioneers and innovators to SME decades ago, where they found a home for their technical group on a new technology called rapid prototyping. Today, 200,000 people are connected with SME in 3D manufacturing, continuing their ongoing commitment of creating the extensive community that they envisioned from the beginning. Welcome to Rapid plus TCT, a place where ideas are born, products are introduced, and visions become reality through 3D manufacturing. Rapid brings people together, paving the way for opportunity and ideas. Rapid is about people talking face-to-face, building relationships, interacting, collaborating, and working side by side with manufacturing's best. People like you. Rapid is accelerating to new heights, connecting us around the globe and bringing it back home. Rapid is forging new frontiers in manufacturing and accelerating technology forward so you can get from point A to point B with amazing innovations. Offering hope, allowing hearts to follow big dreams. Rapid creates endless possibilities that are leading the way for future generations to dream great things that will be brought to life through 3D manufacturing. Rapid advances careers and reinvents industries that energize our economy by adding, not subtracting, making the world a better place. It's the place to experience endless possibilities in 3D manufacturing, the place where ideas come alive. SME is celebrating our strong legacy of supporting Rapid and accelerating the future of 3D manufacturing. Our work isn't done. Join us as we forge ahead, expanding boundaries and discovering new worlds for generations to come.
Ladies and gentlemen, please welcome to the stage Vice President of Events and Industry Strategy, SME, producers of Rapid plus TCT, Debbie Holton.
Good morning. Welcome back to Rapid plus TCT. SME is committed to the medical community in additive manufacturing. We're grateful to the many members and volunteers in the SME Medical Additive Manufacturing and 3D Printing Work Group who give generously of their time and resources to support users of medical and biomedical technology. Members represent medical device manufacturers, clinicians, technology providers, and more, including the Mayo Clinic, Biomet, the University of Michigan, Go Blue, and Materialize. This group helps drive technology to improve and save lives by providing content to address the latest industry developments, identify gaps in standards, and build evidence for additive manufacturing applications in medicine. With the help of this group, SME recently released a white paper detailing the rise of point-of-care manufacturing enabled directly by additive manufacturing. The technology is providing benefits for patients, physicians, and institutions, including better patient outcomes, less time in the operating room, and reduced costs. From surgical devices and personalized implants to bone scaffolds, functioning organ replacements, additive manufacturing is truly changing lives every day. Medical and biomedical are some of the fastest growing application areas of additive manufacturing. You'll see just how far this technology is taking us in this morning's keynote presentation. So now, time for the audience participation part of the program. If you want to get your devices or your phones out, we have another poll for you. In case you missed it, we're using something called Slido. So you can open up the Rapid plus TCT event app, and there is a Slido tab there for you to open it up. Or you can go online to slido.com. And if you're in that app, you use the code RAPIDEVENT, and that'll allow you to participate. That'll allow you to participate in our polling, send questions to the presenters, and some really great benefits like that. So everybody ready? Let's go to the poll. Millions of patients have been directly impacted by the use of additive manufacturing and 3D printing through anatomical models for education or planning, surgical guides for new hip implants, assistive devices and prosthetics, or even an implant made just for you. So tell us, and choose the first one that applies best to you. For medical care, have you personally benefited from the use of additive manufacturing and 3D printing? Know someone who has benefited? Used additive manufacturing or 3D printing to help treat a patient yourself? I know we have some physicians here with us. Or have you seen a story on how patients are helped? Go ahead and keep voting. Okay, we're getting some results in now. Glad to see that some people are personally benefiting from use of the technology. And it looks like we're getting the word out successfully. So a lot of you have seen stories about how others have benefited from the use of the technology. Nice representation from our physicians here as well, who are actually treating patients with the technology, and many of you have friends or family who have benefited from this technology. So thanks for that. Appreciate it. So before we begin today's program, I would like to announce the 2018 Rapid Plus TCT Innovation Award finalists. The two finalists are Additive Industries for the world's first integrated product removal module, and NanoSteel for the 3D printable tool steel for powder bed fusion. The Rapid Plus TCT Innovation Award recognizes the most innovative new products or services exhibited here at Rapid Plus TCT. These are judged to have the greatest potential impact on the industry. So yesterday we had a session where each finalist had 5 minutes to present their ideas in front of our judges. And now we're about to meet the final two. And here's what's really exciting. You will be the judge today. So this is like Shark Tank, right? So you're the sharks, and you'll have the power to vote and select who this year's winner will be. So please help me welcome finalist number 1, who will be presenting his concept, Harry Kleinen of Additive Industries. Please welcome Harry.
Hello, good morning everybody. Welcome on this, some people maybe early hour. Debbie, thank you very much for giving me this opportunity to present our latest innovation in additive manufacturing, the MetaFab 1 product removal module. Additive Industries believes that integration in additive manufacturing really accelerates production productivity in AM and brings this really to the end users and large volume consumer market. Today, we realize this in our MetaFab 1 system, which includes already a number of automated functions. Our industrial AM printer for metal pieces already does automatic powder removal, automatic bill plate handling, has an integrated heat treatment and powder storage for autonomous and operator independent operation. The next step, when a build is realized, we see that there is a next step coming up, which takes also today a lot of manual labor, requires a number of machines. It's often distributed in a complex supply chain, which needs to be managed and maintained. It's a very costly activity, but also because of the lot of the many manual labor prone to operator error. We identified this process, we split it up into different process steps, and we see there are already 15, we identified 15 different steps just to get parts of a bill plate and to get this bill plate resurfaced for the next processing step, for the next print job. And really to bring this, to reduce costs into the AM chain, we need to automate this process. And that's why we developed the MetaFab 1 product removal module. This is a module which is integrated into the MetaFab 1 system, and it provides 4 functions. It does a part cutting, separates the parts from the bill plate by a bandsaw. It has an integrated ATEX-proof vacuum cleaner to remove the residual powder. I don't see my slides anymore. Okay. I'm sorry, the slides on the front monitors have disappeared. Can I get one slide back, please? Yes. The parts are collected in a bin. which is transported by the robot. And there is an automated build plate resurfacing by 3-axis milling integrated. So how does this work? Once the build job is finished, the powder is removed automatically. The robot positions the build job in with the printed parts into the product removal module. Then the parts are rotated 180 degrees, tilted upside down. A separate bin is moved upwards, and a bandsaw cuts off the parts, and the parts are nicely collected in the bin and then ready for transportation to the next step. Then we rotate back the build plate. It's positioned for the 3-axis milling machine, automatically calibrated in height. The milling machine selects one of the 4 tools, which allows you to address different materials. We resurface the build plate, and when it's finished, the robot takes it out and stores it once again in the product removal in the storage module. So in this way, all these steps are integrated in one module, which has a dimension of about 6 feet wide and about 5 feet high. So with this module, we achieved that we could eliminate from this 15 steps, from these 15 different steps, 10 non-value adding steps, resulting in eliminating virtually any manual labor. We reduced the lead time, for example, when you have outsourced activities for cutting the parts of the build plate from 4 weeks to just 2 hours. Reducing the complex supply chain, but also eliminating a lot of stock which needs to be used for filling the pipeline. And finally, the costs are reduced to about 200 euros per cut. This finalizes our proposition, our latest innovation in additive manufacturing. So let's accelerate industrial AM. Thank you for your attention.
Thank you, Harry. Appreciate that. Yep, you're all set. Thank you. So that's pretty amazing, right? As we get closer to full-scale production and additive manufacturing, that's a wonderful development. So thank you, Harry, very much. So please help me welcome finalist number 2 to the stage, Dr. Jonathan Trenkel of NanoSteel.
Good morning. Thank you for that introduction, and thank you for the opportunity to present to you and share with you our innovation in developing a 3D printable tool steel for powder bed fusion. Once again, my name is John Trankel, but this work was done in collaboration with my colleagues you see listed up here on the screen. To provide you with some context for this innovation, I just want to give you a little bit of background about NanoSteel. NanoSteel has been around for about 15 years, and it was founded with the idea of developing steel alloys to meet customer as well as industrial demands. We've done this successfully for a number of products across a variety of applications, some in sheet steel, some in coatings, and now as well as in powders. We have offices and labs located in Idaho, Michigan, and Rhode Island being where our primary powder business is located. We use this expertise as well as its knowledge to address a challenge in identifying a printable, high-performance tool steel for powder bed fusion. Our criteria for success was dependent on properties, of course. For tool steels, you need high hardness, but we also learned from talking to tool and die manufacturers that high toughness is also of value. We, of course, want it to be printable by powder bed fusion, that's the point, but not only printable in a way that it becomes crack-free, unlike the picture you see up here on the slide, but also we'd like to make it easy and be done at room temperature. Next, of course, we want to be price competitive, and we do this with an eye towards the chemistry as well as the atomization process. And then, of course, we always want to be cognizant of the health and safety implications of the powder, being mindful of certain toxic elements, making sure they're not present in the alloy itself. One particular one we have our eye on is cobalt. In some agencies, cobalt is starting to be labeled as a toxin and a carcinogen. So we want to always be mindful of that as we continue to develop new alloys. So when we consider these criteria and then look at the available options for steels in powder bed fusion, we start to look at their deficiencies. So for example, austenitic stainless steels or other similar stainless steels such as 316, while yes, printable, economical, health and safety, they just don't provide the properties that are really needed for tooling. Next, consider miraging steels as well as precipitation hardened steels such as M300 and 17.4 pH respectively. While these are also printable, they only print in a state that's slightly harder than 316, and they really require a significant heat treatment to get the high hardness that you desire. So it's an extra processing step. What's more is that many miraging steels actually contain cobalt, which could be a potential health hazard. Finally, then, we consider our standard typical wrought and cast tool steels such as H13 and M2 and the like. And yes, they have the hardness, but actually they don't have much toughness. But what's more is they really are very challenging to print. In fact, H13 typically requires temperatures around 500 degrees Celsius, which just adds cost and production time. So with all these deficiencies in mind, NanoSteel does what NanoSteel does best, and we developed Builder Metal L40, specifically formulated for powder bed fusion that satisfies all these criteria. What is Builder Metal L40? It's a tool steel with a remarkable combination of high hardness as well as high toughness in the as-printed state, as exemplified by this graph here. You'll see that H13 does have slightly higher hardness, but keep in mind, as I mentioned before, it has nominally no toughness, so it's very brittle, and also it requires significant resources, intensive resources to print at elevated temperatures, whereas L40 can be printed at room temperature. Also, we get these properties by just printing at, like I said, at room temperature, but we can also enhance them by standard industrial heat treatment practices. In some of these surface heat treatment practices in particular, we can get hardnesses in excess of 70 HRC, so significant improvements. So what does this mean in terms of benefits and values? It means exceptional tooling lifetime made from affordable powder, exceptional tooling lifetime in your tools made from affordable powder, but also tooling, die, and molds made within hours, whereas traditional machining methods might require months lead time. Not only that, it also enables complex geometries that were unimaginable before, that could not be machined by using powder bed fusion processes. So we also have developed parameters for all the major machine manufacturers for L40. So while NanoSteel is a material supplier, we also have the AM expertise to take the powder, which you see in the containers here, and actually work with you to develop and use it and integrate it into your tooling or die or mold design, as you can see in a picture of a threaded bolt die here. So in this way, we're really revolutionizing the tool, die, and mold industry and what can be accomplished in terms of geometries and capabilities. So with that, I'd like to thank you for your attention, and I invite you all to stop by booth 434 and learn more about L40 and some of our other NanoSteel products. Thank you.
Thank you so much. Thank you, Jonathan. I guess we should call you the man of steel, maybe. I don't know. But great. Okay, so Sharks, it's time to start voting. So make sure that you're on there and voting for the application that you think is the most transformational, revolutionary to our industry and to additive manufacturing and 3D printing. So as one of the fastest growing additive manufacturing and 3D printing application areas, more growth is expected for biomedical and medical applications. More than 97% of medical additive manufacturing professionals expect the use in applications in regenerative medicine to continue to grow. I'm pleased to introduce our next speaker, who many of you know. She has been part of the additive manufacturing industry since the rapid prototyping days and currently serves as SME's industry manager for medical. In this role, she guides SME's medical industry strategy. She's also currently the vice chair of the Additive Manufacturing Standards Collaborative and sits on the ASTM F42 Executive Committee. She's truly an expert in her field. Please join me in welcoming my colleague and friend, Laura Lynn McDaniel.
Told you a little earlier about the SME Medical Additive Manufacturing 3D Printing Work Group. I'd like to tell you a little more about this dedicated group of volunteers whose goal is to identify challenges to increasing the use of these amazing technologies to impact even more patients. They represent companies that manufacture devices, develop technology, clinicians like our speakers in a few minutes, as well as researchers and others dedicated to helping people. Their collaboration has resulted in new tools and new information sources for anyone using the technology, including developing a resource page where we've gathered all of these on the SME website. One of the first ones that we published last fall was on workforce development. It was a white paper describing the need and why there's such a critical need for skilled professionals that combine engineering and medical knowledge. We developed workforce development job descriptions, competency models that are freely available to download for anyone to use. And while I've been here today, this week, I've heard several of our work group members talk about using them to post new jobs to fill those needs. We also conducted a survey late last year, and took part of that to talk about the exciting work that's going on within hospital settings, the radiology-centered point-of-care manufacturing, which we'll hear a little bit more about from the Mayo team. And today, we're announcing our first ever annual report on medical additive manufacturing, covering device manufacturers, point-of-care manufacturing, and anyone impacting patients with the additive manufacturing. The first number I want to share with you is that 97% of the responders expect an increase in the use of additive manufacturing for medical applications. And they didn't just expect an increase. Over half expect more than a 10% increase in 2018. And they expect it across all the major categories of applications within medical. And it's not all good news. They do have some challenges. The top challenge remains the regulatory environment. Materials is another challenge high on the list, as we heard from some of our speakers this morning already. And we also have a, in case you missed it, section to highlight what has happened in the last year. It includes many of the collaborations, including the announcement last November by Materialize and Siemens to work on a workflow that creates bottlenecks within the hospital. Some of the regulatory activities, including the release of the FDA's technical guidance for device manufacturers. Organizations that are working in this area, including the DICOM Standard Work Group 17, the RSNA 3D Printing SIG, and our own work group and the activities they're doing. Some new materials that were released, particularly in the dental area, and an exciting area of developments to watch that could have impact for the future. So this report is free to download at our resource page. This has been running across the bottom of the slides today, so I hope you had a moment to pick it up. So before, I'll leave this up here for a moment, but I want to call out one of the companies that have several very active members within our work group, and that is Materialize. And I'd like to thank Materialize for sponsoring our keynote this morning and introduce to you Peter Lays, the chairman of Materialize. And before he steps up, we'll show you a short video.
"3D printing has evolved into a true industrial manufacturing technique, adopted by an ever-growing and wide range of industries. But have you ever wondered about the technology behind these innovations? Can you imagine how designs for 3D printing develop? How they're made printable? And how you make sure you only build parts that fully meet your expectations? How you can scale up your production? And how all of this can meet your industry standards? For over 25 years, we've been building the software backbone for all businesses and industries that want to apply 3D printing in a professional manner. We've become the trusted partner of leading machine manufacturers. We've co-created platforms that are the engine of disruptive innovations that change the rules of businesses, that change how factories run, and have an impact on people's lives. And we keep pushing the boundaries of 3D printing because we believe that extraordinary technologies need extraordinary software.
Ladies and gentlemen, good morning. A warm welcome from Materialize to this morning's first keynote speech. In the next 10 minutes or so, I am supposed to formally introduce a very important partner of ours, Mayo Clinic in general, and more specifically, Dr. Jay Morris and Jamie Alexander. As you know, I'm also supposed to sneak into that formal introduction some very nice words about this wonderful 3D printing pioneer that I am representing, Materialize. But why would I want to do that? Why would I want to spend your valuable time on introducing institutions and individuals that you all know very well? And even if I would want to do that, even if I would want to take your time to introduce Mayo Clinic, Materialize, Dr. Jay Morris, and Amy Alexander, would I be able to do so? Would I be able to do that without doing great injustice to the many accomplishments and the very extensive CVs of these very important institutions and players? I would not be able to do that. So here's what I decided to do. I will change the script, and I will introduce you to somebody totally different. Ladies and gentlemen, I would like you to meet Nathalie Dufault-Danjon. Nathalie is a French citizen, happily married, a mother of two. Roughly 2 years ago, on May 17th of 2016, Nathalie attended the wedding of her niece somewhere in the south of France, together with her husband and her two beloved kids. And what was supposed to be a lovely long weekend gathering with family and friends turned into a nightmare. The morning after the wedding, a heavily disturbed member of the bride's family rushed into the hotel's breakfast room carrying a hunting rifle. When he left the hotel only moments later, 6 members of the family were killed and many more were seriously injured, including Nathalie. Nathalie, ladies and gentlemen, spent 6 months in coma, woke up, and started working on her recovery. One particularly nasty bullet had hit Nathalie in the shoulder, completely destroying the anatomy of the joint. As a result, she lost all mobility in her shoulder. During the recovery process, Nathalie refuses to just fight for revival. She wants to regain full mobility. So in a period of less than 6 months, she visits not less than 12 different surgeons. And she starts studying. She spends so much time on the internet that even the algorithms of Google and Facebook get confused. She starts reading journals, medical papers. Frankly, She has probably read more medical papers on shoulder trauma than, with all due respect, Dr. Jay Morris and Amy Alexander will ever read in their entire professional careers. She becomes an expert. But still, every time she talks about these innovations that she stumbles upon during her reading, every time when she talks about the potential of 3D printing to all these various surgeons, all these various hospitals that she's visiting, she gets the answer that you have all heard before, and some of you may even have used that answer. 3D printing is at a too early stage, Natalie. It's too risky. There's not enough clinical evidence. It's too expensive. Even 3D printing will not be able to help your complex case. It's a gimmick. But Natalie does not give up. She pushes, and eventually she is referred to a pioneer, a crazy believer in innovations. Just like Dr. Jay Morris and Amy Alexander, whom you will meet in a couple of minutes, are also pioneers and believers. Dr. Brice Viard, an orthopedic surgeon at the University Hospital of Dijon, is the first person to give Natalie hope. Dr. Viard, who works regularly with the clinical engineers of Materialise, just like Dr. Jay Morris and Amy Alexander do, gives us a call. And Materialise and the University Hospital of Dijon decide to join forces. We decide to join Natalie in her quest for shoulder mobility. And here's what we did. We deployed our Mimics technology to develop a 3D pre-operative surgical plan, helping Dr. Viard to virtually plan his upcoming intervention in the greatest detail. We produced a physical anatomical model of Natalie's shattered joint for diagnostic purposes, but also to facilitate the communication between the surgeon and his patient, who had, as you know, in the meantime become a true expert of shoulder trauma. We also applied our patented Glenius technology to produce a 3D printed personalized shoulder implant for Natalie. And finally, we 3D printed surgical guides, allowing Dr. Viard to place the implant in the most accurate and precise way possible. Several months after the operation, Natalie regained significant mobility in her shoulder. Admittedly, it's too early to ascertain that there will be bone growth in the implant, but the short and mid-term outlooks are very positive. Today, ladies and gentlemen, Natalie is able to perform again simple but very important tasks, such as making the bed for her children in the morning and giving her kids and her husband a well-deserved and well-balanced hug in the evening when they come home again. For those of you who are interested, Natalie published a book towards the end of 2017 about her journey for recovery. The title is Shattered Dreams. Ladies and gentlemen, there are not that many people like Natalie who are as strong, as determined, and as stubborn. There are not that many patients who do not take no for an answer. In some instances, probably rightfully so, patients accept a no. But in every instance where a no is accepted too lightly, in every instance where a medical innovation is overlooked, a life is being destroyed. Children are being denied the human right to a bed that has been well made in the morning and to a well-balanced hug from their mother in the evening. And that is why we as an industry have to be as stubborn, as strong, and as determined as some of the patients that we can help, as Natalie. We have to, as an industry, join forces to break the many barriers that deny patients access to innovative solutions such as the one that helped Natalie. And that is what Mayo and Materialize have been doing. And many of you are doing. I see some representatives of DePuy Synthes J&J in the room with whom we are collaborating especially on our shoulder solutions. Empowered by the Materialize tools and technology, Mayo has become a point-of-care manufacturer for anatomical models, is using virtual surgical planning as much as possible, and in certain cases also deploys Class II medical devices such as our osteotomy guides. So it is with great pleasure and pride that I introduce to you this morning our next two speakers, Dr. Jay Morris and Jamie Alexander of the Mayo Clinic. And I can tell you, Jay Morris and Jamie may not be as strong and determined and stubborn as Natalie was, but they come as close as you can reasonably get. Before Jay Morris and Jamie find their way to the stage, I would now like you to watch a small video about the Mayo Clinic's activities in 3D printing. Thank you so much, and enjoy the rest of your day.
Mayo Clinic is actually founded by a partnership between the Franciscan sisters and William Morrow Mayo and his two sons. Those founders' values of caring, of service, became slowly codified over time into what we refer to as our model of care. Today, we really are standing on the shoulders of giants who have created a whole series of ways to care for patients. Teamwork in the sense that people are stronger when they work together, they're smarter when they work together. Our integrated medical records, so the efficiency can be extraordinary. The physicians are salaried at the Mayo Clinic, so physicians make decisions that are best for the patients. No field changes faster than medicine, but the things that are never going to change are the core attributes that make us unique and special. Any employee at the Mayo Clinic will tell you that their job is to make sure that the needs of the patient come first. And that's really the Mayo Clinic experience.
This is a time of enormous change in healthcare, and that provides a very strong institution like Mayo Clinic with a very unique opportunity to lead and create the future of healthcare. Our commitment is to provide a seamless patient experience, providing exceptional, affordable, whole-person care for patients across the nation and around the world. That's the next century of healthcare at Mayo Clinic.
That was good. Thank you all for coming here. We're really proud to be here. We thank Materialize and SME for inviting us here. It's quite an honor for us to be here, particularly me as not an engineer. I'm kind of the doctor in the house. So I'll let you know up front, there's going to be a few intraoperative videos. So if you don't like seeing blood or flesh, and you might need a doctor because I can't give the talk and deal with you, I'll tell you and you can just look down. It's okay?
Sounds good.
All right. So we're going to talk about the rise of point-of-care manufacturing, which I think is the term now for what we do. And we're going to, in the app, there's a Sketchfab link, and you can download a couple models from Sketchfab, like this model, and some rhabdomyosarcoma models, and some models we're going to talk about. We'll talk a little bit about Mayo Clinic and its integrated team approach. We'll talk about medical 3D printing, how we use it clinically, and then a little bit about the future. So as you just heard, Mayo Clinic is a fairly large institution. The mothership is in Rochester, Minnesota, but we're really in about 6 states with 5 schools, a lot of employees, and we saw 1.38 million patients last year from 140 countries. It's an $8 billion enterprise, and it reinvests almost all of the money back into the Mayo Clinic so we can further our mission. There are affiliated care practice networks around the country as well. It's an integrated team, and what that means is no matter if you're on the floor seeing a patient, if the video will run, we'll see. We tested this out. I will say we tested this out, and all the videos did run. Whether you're on the floor seeing a patient, that there's a team of people there. There might be a pharmacist on your team, a medical doctor on your team, multiple people there. And in the mornings, we have tumor conferences or multidisciplinary care conferences that go over complex cases. And there might be radiologists there, radiation oncologists there, neurosurgeons there. There's a whole team of people there, all experts in their own field, being asked questions. What should we do for this patient? What's the best for this patient? Maybe you could advance to the next slide. We're not. Hope they stop the timer. You know.
Yeah. Pause.
Yeah.
Okay.
So we 3D printed a lot of stuff over the years, but we really started small. And we started with something incredibly complex, which is what we're going to get into. And while we were doing that, we needed the help of an engineer, which is why Amy and I are both up here talking, because without Amy's skill set and the skill set of a lot of engineers, particularly from Materialize, I know Materialize was just here talking, but they have been a wonderful partner to us. We call them, we pick up the phone. I see Todd nodding his head because we call them a lot and ask them, how do I do this? How can I make this happen? There's a surgeon or a patient who has a need. How can I make this happen? And they're very responsive to us, so we're very appreciated from the people at Materialize throughout their company. Several of the vendors also help us along, from 3D Systems and Stratasys and Form Labs, who are all here, and they've been an incredible resource for us because we had to figure out at some point how to put industrial equipment inside of a hospital. And those two things don't always go along, because to put powders and polymers and lye baths and things in a place where there's patient care activity happening requires a lot of facility work. And the vendors have been very good to us in helping us build this institution inside the hospital at Mayo Clinic. We thought it was really important to put it inside the hospital because there was a study that was done back in 1977. It was done by Allen. It's called the Allen test. And he showed early on, this is a long time ago, I was 6. I know some of you are probably 3, older than me, hopefully. They're working on it. So early on, he showed that the further you are away from your colleague, the less integrated your business was. That if you were 6 offices down, you were less productive. If you were on another floor, you barely never talked. And if you were down the street, you would never see each other ever, even if you had the same business mode. So we thought early on that we had to put the 3D printing center inside the hospital, because we had a couple fused deposition modelers at the time, or extruders at the time, but they were, you would think it's just down the street, 3 minutes down the street. But to really busy surgeons, that might as well be in another planet. So one of the benefits that we did is put all this equipment inside of the hospital and allowed the surgeons to come upstairs in between cases, or their residents to come in between cases and have an open discussion. Maybe Amy can talk a little bit about that, because she's there a lot of times.
Sure.
I'm an interventional neuroradiologist. I treat tumors through ice and heat through needles. So a lot of times they come to see Amy.
So Amy Alexander, biomedical engineer in the anatomic modeling lab in the Department of Radiology at Mayo Clinic. We are so thrilled to be here, and I'd love to talk to you about how having an engineering role in a clinical setting is just so different from being an engineer and a device developer or in a different industrial setting. The relationships that I'm allowed to build with radiologists and surgeons are invaluable and contribute so much to development and innovation inside the hospital setting, where it's faster and it's more alive, I would have to say. I think they're getting closer to bringing us back, Dr. Morris.
Yeah, we're almost online.
Yeah, almost online.
I could talk about 3D printing all day. That's what we do every day. It's better with the pictures, though, I guarantee it. Nobody wants to just see me walk around stage waving my hands. I'm not as good as the folks from Materialize. I mean, they were born for it.
Yeah.
And the folks from SME. All right. We're back. I think. I can see it.
We can see it. Can we move it forward?
How many people here, by a show of hands, are doing medical 3D printing?
Wow.
That's a lot.
That's awesome.
How many are you associated with a hospital? Also quite a number. Okay. I think they're going to show it on the big screen.
Oh, I think we're back. So you were talking about the integration.
Oh, there you go. So we were talking about the multidisciplinary nature of the clinic. So some of these are stock photos from Mayo, but some of them are just pictures I take on my iPhone as I walk around, because it's hard to capture when a group of people are meeting just outside of an OR and everybody's talking about something they're about to do to somebody. And that multidisciplinary care rolled right over into 3D printing. So when we incorporated 3D printing into the hospital, nothing changed about the type of care we delivered, that it was an interdisciplinary form of care where people gathered around and talked about the patient. Now, they're talking to the model, but in their mind, they're talking about the patient. Luckily for us, we've had a long-standing history of engineering at Mayo. So, Amy, I'm going to pass the pointer to you, and she could talk a little bit about engineering.
Thank you. So engineering at Mayo Clinic is not new. Image processing at Mayo Clinic is not new. The engineering division at Mayo Clinic has over 70 biomedical, chemical, electrical, mechanical, and software engineers. The biomedical imaging resource is made up of over 20 senior image processing specialists who design in-house image processing software for use with radiology and research. This is one of our favorite pictures because it's a random Tuesday peeking into our tiny lab before we had grown. You're looking at radiologist, surgeon, 2 biomedical engineers, 1 from Materialize, and 2 technicians. So in this small space, we're all very close in proximity, like Dr. Morris was saying about the Allen effect. We're very close. We're talking, we're thinking, we're kind of stirring up ideas as we go along.
That's right, and this happens randomly all the time because we're right near ENT and we do a lot of ENT, that we'll have one ENT surgeon walk in and before you know it, there's 5 people in there. So we really had to grow over the time, and there's people coming and picking up models, dropping off models. This one broke. Surgeons aren't the most delicate-handed people with the models, at least. And we've incorporated engineers into our system clinically, which is different because we have a lot of engineers that do all sorts of things for us, and glass blowers, but we needed people in the hospital where the doctors were. And this group of people that are shown here, they're medical physicists, cardiologists, cardiac imagers, neuroimagers, surgeons. There's a whole host of people that make this happen. And eventually we were printing a lot of things, and we had to say this is not just a one-off or average, we're just doing case reports. We have to make a clinical system and integrate this into our model of care as an enterprise, not even just in Rochester. So when we talk about medical 3D printing, it's good to talk about where we started. And where we started was something very complex. The initial case for 3D printing at Mayo, and it continues to be this way. There was a clinical problem that needed something extra than what we could give. And what we could give at the time was imaging. So there was CT images of these children. There was all kinds of images done of these children. But in the end, my partner, Dr. Jane Matsumoto, who runs the lab with me, the surgeons would tell her, only you understand what's really going on, and we need to take what's in your head and get it out here to the rest of us, because it's incredibly confusing. Even with these nice illustrations, there were still people drawing on boards, hanging up x-rays, moving around the room, trying to understand the anatomy. And what they asked for was, could you make us a liver? Of which this was the first medical 3D printed object at Mayo. And they stopped talking to the wall and they started talking to the liver, because that is where they were going to do the cuts on the children. And there's a whole team of people in there, so you want to have a really good plan before you go in there with 50 surgeons to say what every step is going to be. So there were months of meetings and training to go over this, and you can put your head down if you don't like to see any gore, because somebody is going to have to look down eventually when all is said and done, and one person is going to have to cut the liver and say, this child is going to get this part of the liver and this child is going to get that part of the liver. And if we do it wrong, it could lead to the fatality of one of the children, which is the really high cost of separating twins, is one twin dies. And then you have two children that you have to take care of in the operating room. Well, once you do one, you get a lot of press. So then if there's another twin that's born, they immediately know who did the last one. So, but the same thing happened. We made models, and the surgeons gathered around and talked about the models. And there's my partner, Dr. Jane Matsumoto, with the purple tag on. From there, one of our spine surgeons saw the model, and he thought, wow, I only work in pediatric spine. That would be great. But really, our lab is as old as these two girls, because they were separated in November of 2009, or 2005. That was our first thing we 3D printed, and as they've grown up over the years, our lab has exponentially grown because it provides the same value as it did back then. From twins, we quickly went into congenital scoliosis, doing all forms of planning for scoliosis, and Amy does some of the pedicle screw trajectory planning. Mm-hmm. So some of this work where we're planning screws and putting screws in before the surgery. So before the patients even got into the operating room, so they don't hit the spinal cord with the screws, because some are really complex, like this spine sticking out of the back of this person, who somebody is going to have to go in and put a bunch of screws in and not further harm them. So one of the questions we get all the time is, in radiology, why can't you just look at the 2D images? We do more than 1 million exams a year. We purchase an enormous amount of equipment. Someone told me one time that we have more scanners at Mayo Clinic than they do in the entire country of Canada. I've never validated that, but certainly it's a rumor. So why can't you just look at these images? And the images are getting better. These are cinematic images from Siemens, which we can get now in a click of a button. So under 5 seconds, if I have a head CTA, I can get that image now. And that's going to be on the market. So why can't I just use these great images? Well, one of the problems is you can't hold an image. You can't touch an image. You have no idea how big that is. It could be as big as the Sketchfab on your phone or as big as that screen. And unfortunately, a surgeon is going to have to operate on this child who has a severe deformity. And there's very binary decisions the surgeons make when they get the model, like how am I going to put this patient on the table? How is anesthesia going to intubate this patient? Because this is a severe abnormality. And until the surgeon gets the life-size model in their hand, they really don't know how to answer some of those questions. And sometimes a lot of that happens in the OR, where you say, how am I going to put them on the table? Oh, I can't go like that. They bring the models to the OR sometimes and just position how the person's going to be lying there, because you can see the back of the head is in the way of most of the things you have to correct in this child. There's a bit of haptic perception that goes on when you touch an object. So if you're holding your coffee cup or holding a fork, you get much more brain activity, even in the visual cortex, than if you just saw a picture of your cup or fork. So there's haptic perception. Then there's things we learned from the model. There's about 5,000 things you could focus on in this child that's wrong. But we learned things when we print it out, because an anesthesiologist noticed this person has a severe tracheal stenosis. It's going to be difficult intubating them. And if you're awake intubating somebody and you can lose access, it's a very frightening thing to happen. So they've asked us in these really congenital scoliosis, just because we're in the same place as them, can you give us the airway? We would have never thought about that when we were printing bones. Well, we should put the airway in there because somebody might want to intubate the model. It wouldn't have happened. And I think 3D printing it shows itself best when I usually ask surgeons early on, what did you like about it? And they said, well, there's a lot of unknowns before I get in the OR that I can only know once I make a major incision and loop a lot of things off. And when you 3D print this object for me, it makes things known to me, because if I see someone in the clinic, I know something's wrong. I could get an x-ray and I can see something's wrong, but I don't know the details about it. A CT scan gets more confusing because now you can see the abnormalities, but it's confusing. You can make 3D volumetric images, and then you have to get an MRI, and then you have to put all that data, the clinical visit, the CT, the x-ray, the MRI, in your head, make a life-size 3-dimensional object and operate on it. It's almost impossible. But when you hand them these little objects and say, this is that spine, every surgeon, every place we've gone, every lab we've helped set up at different institutions has the same reaction. Oh, I know what I'm going to do now. Oh, I know where I'm going to put them on the table. It's not particular to Mayo Clinic. And this patient, you can see there's a lot of screws that had to go in. There's a lot of metal that had to go in to fix this patient that had a severe anomaly that was pinching their spinal cord and inhibiting breathing. And he did so well that he was in the halo. People hunt in Minnesota and in the Midwest. So his dad built him this shed because they told him you cannot put a rifle against your shoulder while your spine is healing. And he still wanted to hunt. So here he was he sent us these pictures saying the gun is not next to me, but he was still pulling the trigger, and he was happy as can be. That happened because of a whole group of people. Not me, not the 3D printer, not the surgeon. The whole group of people came together to fix that problem. There's some deer gore, too. It's not all going to be human gore. So we went from spines very quickly into tumors, and you can see that this patient's got a very complex tumor. There's a large, this is the cervical spine, so the part that connects to your head, and you can see there's blood vessels that feed the head. There's the clavicle that might have to come off. Somebody is going to have to cut a lot of bone out of there to get this tumor out, because you can't touch the tumor while you're taking it out, or else you'll have a recurrence, and there's going to be a huge hole that has to be filled with something. And they might have a stroke while you're doing it, because you're going to have to take care of some of the vessels in there. So there's going to be a vascular surgeon, an orthopedic surgeon, a neurosurgeon, an anesthesiologist, all who speak different languages taking care of this patient. And the model served as a common reference for them to all come together and talk about. And this is Dave Daniels, one of our neurosurgeons, who just came back from talking to the family. So bringing the model out, saying, this is your girl, this is your daughter, that spine, and this is why this risk is there. And this is what I'm going to do. And it lets him do that better. So once we started doing tumors, really, the barn doors were open, and we couldn't go back, because then every tumor surgeon started hearing, oh, they can 3D print a model with the tumor in it, and it was really helpful. The way we do most of this, and Amy alluded to this, is we take some imaging, and we protocol that imaging, we put it into software. Now, we use mostly materialized software where we work, because one, it's FDA approved. It just got another FDA approval for Insight, and our institution said, we want you to use FDA approved software. We can't put freeware on the electronic medical record, and they've been an incredible partner with us, like I said. A lot of the innovations you'll see is from us calling Todd or Kevin and saying, I'm stuck. Can you help me? And they do. We segment the data, and then we send that segmented data into 3Matics and create a mesh, and then we print it. And right now we have Objet printers, we have FDM printers, we have Formlab printers, and we have ProJet printers. So that's inside of a hospital. We have some in the engineering too, and then we're looking to put in SLS now and some other technologies for this year. And then we have to post-process it. And just like you, we kind of want our printer to do everything. We want it to be clear because we need clear sometimes. And we want it to have color because we need color sometimes. And we want it to have clear and color sometimes. And we want it to be flexible. So we need to try a different printer for flexible material, because sometimes we're implanting things or doing simulations on something that is flexible, because the human body is not rigid outside of bone. And even bone is not as rigid as some of these plastics. And sometimes we need sterilizable. Look away. There's going to be some of this in the craniomaxillofacial work. And then there's metal. There's actually talk about bringing metal in-house, but it's not there. So if we look at some of our clinical use case scenarios, the first big one is craniomaxillofacial. And one of the reasons is because your face is your entire identity. Any one of you could be missing a finger. In fact, we had a fellow that was missing 3 fingers that I surface scanned and made sterile gloves for. Half our staff didn't even know he was missing 3 fingers. But if he had a lazy eye, or a jaw or a facial palsy, you better believe everyone knows because you're set to look at facial symmetry. And it tells your emotions. It tells you who you are. A lot of it comes through your face. So if you're going to take somebody like this, you need to repair them to a state of not just cancer-free, but a place where they can go out in public and they can interact with society. I was trying to click it. I wasn't trying to leave it up there too long. You have to put them back to a space that's the same person where he can go out and feel like a normal participant in society. And 3D printing has helped a lot. Here's a woman who just gave birth who has a lump on her mouth, and that pink thing that's growing up into below the orbit there is a tumor. And this is one of the reasons a radiologist has to be involved in this, because only the neuroradiologist is going to know how far the tumor goes. And if you cut too low, it's 100% recurrence. If you don't radiate high enough, it's 100% recurrence with this tumor type. So her chance for survival, 5-year survival, is a gross total resection. And the surgeon, though, doesn't want to take her eye out. I mean, you only want to stop at some point. So they ask for a model just for simple, we're going to cut here, and this is how high we have to go up. But there's a level of trust. You know, they trust me that that model's accurate because I segmented it and I know where the tumor goes because I'm their neuroradiologist. I mean, I know about 3D printing and things, but at my core, I'm a neuroradiologist. And it was incredibly helpful to them. I said, how did you use it? They said, well, we cut the scapula and we put the scapula in the maxilla. And then I said, then what'd you do? And then they said, oh, we bent all the plates, which I would have never thought of because I'm not bending plates as a neuroradiologist. But they said, I said, what did you like the best? They said, we could bend the plate on the model. A lot of times bending a plate on someone's face who's half taken off is very difficult. So there's the model, and it fits, and the teeth are planned in that little piece of scapula so that she can look normal eventually. Most of the mandibles we take out are brought, the leg bone, the fibula is brought up, and the way that we do that is you cut out a piece of the mandible, as you would expect, with the teeth, because it's usually squamous cell carcinoma. We take out a piece of the leg, and that piece of leg has to go up and fit in that spot, and the plates have to be bent to it. Now, they used to freehand all of this. In fact, there are places that still freehand this. They draw on paper, they make sketches, they cut too big, cut too small. They say, oh, it'll be okay, give me some morselized bone, I'll put it in there. And then send them to the guy who does the teeth, who then complains that the bone was put in wrong for the teeth. So it wasn't a very integrated approach initially. And one of the things we said is, not that we were going to come up with virtual surgical planning, because that had already been invented back in 1994, I think was the first paper, but we were going to try and bring it in-house, which means we needed an engineer, because as much as I can segment and know anatomy and pathology, I'm not going to know tolerances of screw threads and distances. So I'll let Amy talk about the engineering component of that.
We're going to get a little technical, but I think you guys are my people, right? The engineers. All right, so I put kind of our input function output diagram up there because I feel like that's our home. The input for medical modeling is going to be imaging, whether it's CT, MRI, surface scan, we're playing around with ultrasound. And then the next step is to do something to it. We use materialized software to segment the anatomy and then create 3D parts that we go ahead and print. And then what is the application? What are we doing with these models? Are we showing them to the patients and the families to improve comprehension? Are we using them for surgical planning to get our entire team on board for the surgery? All of that is limitless, and we come up with more things the more surgeons we talk to. So here's just a kind of example from, I think it's 3D Systems website, of the different segments from the fibula that are being brought up into the mandible to reconstruct the mandible after resection. Just a bunch of positive things that come from in-house clinical engineering, where we're sharing ideas between the radiologist, the surgeon, and the engineering team.
And I would note that the one that's not up there, but the surgeons like the best, is they go home earlier. You can add that to your local surgeon.
They do like that, yeah. So we're going to talk about modeling. Specifically, I'm going to show you a case that really exemplifies a lot of what we do. Okay, there are a lot of steps. It's not push button, as all of you know. 3D printing is not like 2D printing. You don't push a button and something comes out. There's a lot to take into consideration. First step is always going to be the imaging. And so for a reconstructive case like this, you have to get the imaging of the facial region, but you also need to get the lower limb. And the surgeon needs to know to order those with the correct protocol so that the imaging data is sufficient for anatomic modeling. And that's one of the bottlenecks and drawbacks that we've had over the years, is that they don't quite understand what makes an imaging set good. And so we have to kind of educate them. We need a thin slice, a nice reconstructive kernel, et cetera.
And that looks really nice because there's no dental artifact, but 75% of the people have dental artifact. So
yeah, I chose that one.
We
on
have
purpose.
a certain protocol just for this.
Yep. And so here is just showing even just segmentation to us is important for the surgeon to see the difference between tumor and healthy tissue, bone, et cetera. Once we isolate the anatomy, we can move forward and have the surgeon come in, schedule a time with us. It can be 5 minutes, it can be 3 hours, depending on what they're looking to achieve with this virtual surgical plan. But they'll come in and sit down right next to us. We each got a coffee. We're looking at the imaging. We're planning the surgery out in a very low stress environment. We're playing around with cutting planes, osteotomy planes. We're figuring out how is this surgeon going to resect this piece of bone and then reconstruct it the best way possible for this patient.
And again, they're not worried about is that the margin of the tumor, because tumor margins are very important. They take for granted that we're giving them that.
Mm-hmm. Another thing that we've done in the recent past is invited the prosthodontist and the dentist into the virtual surgical planning session. So we're effectively getting input from all teams at the same time, instead of the surgeon making a decision about the segment placement and then the prosthodontist having to deal with that. So everyone's kind of learning a little bit more about what's required for the best possible care for the patient. Oh, I like this one. So we started creating the reconstructed mandible STLs, sending them out for a custom plate design to a partner called KLS Martin. They will 3D print a titanium custom plate for us and send it back, deliver it to the surgery the same day. So our plan is being integrated into a third-party plate design. This is also an interesting slide. There was one day we were kind of hanging out in the lab, and I looked at the surgeon. I said, how do you know that when you bring those segments from the leg and put them in the face that you're putting them in the right spot? And he kind of went, yeah. I was like, I think we can do better than that. So I said, what if I printed you the native remaining mandibular bone and an outline, I think I can go to the next one, an outline of the segments that you can then use to pre-assemble the fibular segments to the model and to the plate, and then move that entire assembly into the mouth. We also make fibular guides so that we know that the segments that we're taking from the leg are going to work perfectly for the plan. Of course, we get surgical approval. There aren't often times where they come back and say, no, that's wrong, let's change it. But once in a while, I do get a call on a Friday at 5:30 from a surgeon who wants to WhatsApp with me and talk about potentially changing a plan. That does happen, nights, weekends.
Yeah.
Yeah.
Great.
But then we 3D print. Our 3D printing process follows the instructions for use. That's an important thing for in-clinic surgical technology. The parts that we're creating in-house must be sterilized appropriately for proper use in surgery. So there's my fixation tray. Again, and it's such a simple concept. The parts are already there. We print it in a autoclavable, sterilizable material. They can pre-place the segments and plate them outside of the face where they don't have a lot of wiggle room. And then once they're happy with that plating, unscrew it from the fixation tray and move it into the mouth. Again, the prosthodontist is brought in right then and there. There's no wait 6 months and then we'll try to get teeth to fit in there. They're part of the team. It's part of the overall multidisciplinary approach to patient care.
So we were lucky enough that they filmed this fibula. Look away if you have problems. Sorry, I was a little late to that one.
Look away.
But, you know, they filmed this not for 3D printing. In fact, I don't think Eric Moore says the word 3D printing in the entire thing, but he says guides. And it was funny because he flipped it around right at the beginning of the video because the knee and the ankle we printed on there, but These are being screwed onto the bone while it's still connected to blood supply, and then here they are, pre-bending the plate. You'd think like, oh, well, that doesn't look like much. Well, it's much when you don't have a mandible and you're trying to guess what shape that is. And here they are with the pieces. They're just wedges of pieces held together, with some meat that's still on there because it's a vascular flap. It is. I mean, it's a vascular flap, meaning it's going to be hooked into a blood supply. That's why it's so successful, because it's living bone that you're putting in there. And it can get radiated. So it can get radiated with 70 gray. 70 gray to the face is not trivial. So when people say, oh, we're just going to put a piece of plastic in there. Oh, we're going to put an osseous implant in there. Oh, we're going to put whatever in there. Well, that whatever has to stand up to 70 gray radiation. And I can tell you we've seen a lot of patients with holes in their skin and that implant showing. So it's important that it holds up to radiation, which is a lot of things that I wanted to give a shout out to someone in this part. So.
Okay.
One of the nice things that we do, and Amy does, is I said, what if we took the specimen out and then we surface scanned it, which probably from some of your looks, when you said like, oh, that's disgusting, you wouldn't think let's surface scan it. But to us, where we teach radiology pathology, we have hundreds of thousands of pathologic specimens sitting in formalin that we can't interact with regularly unless go down to wherever all the formalin is kept. Certainly couldn't bring it into this room without a lot of approval. So this was the first thing we surface scanned, this ameloblastoma, and then, the clicker?
Yep.
Oh, so then we surface scanned it, and we were able, it's not perfect color, but that's really good compared to like blue, right? Because the thing we printed was blue. And then we were able to print a skull with the ameloblastoma in it, and then there's Amy.
Yeah, this was a particular geek out moment for me because I had never seen a surface scanned specimen aligned with a segmented bone from CT. And so we had previously printed the tumor. If you look closely, the blue tumor is a little bit larger than the surface scanned resection. And at first I thought, oh, maybe our segmentation margins were a little bit off. And I mentioned it to the surgeon, and he said, no, it's devascularized. The blood's out of it, so it shrunk down. And so it all kind of just clicked and came together. So
you'd say, well, how does a neuroradiologist get any surface scanning? Well, I can tell you it was right here. Michael Raphael's sitting right there. He taught me. I went to a symposium the day before Rapid started, and he taught me how to surface scan, or what a surface scan was. And that's him on the side at Mayo Clinic, because we were trying to do photogrammetry of premature infants. I don't know how to do that, but I know someone who does. So I called him up, and he's been a great asset to us at Mayo Clinic. We want to know surface scanning. People that are involved in medical modeling have also been great assets to us. The people at Materialize we talked about, but there's people at 3D Systems. And before their 3D Systems bought medical modeling, there was Andy Christensen. And Andy has been a great friend to us. In the early days, when we just started, someone could always say, oh, I've been doing that for years. Oh, that's low-hanging fruit. Oh, I've been doing that for a decade. He never said that. He always was supportive and helpful, and I thought it would be remiss without mentioning him because he's helped us in so many ways. This was at last year's Rapid. That's Andy Warhol, and that's Andy on the Andy Warhol couch. So if you don't know Andy, you should just let that picture sink in. We're trying to set up now a way where we surface scan all the pathology that comes out, which is going to require a process. Because if you take somebody from L4 down to the sacrum and take that out, that means that person lost all bowel and bladder function, is paralyzed from L4 down, has a colostomy, no sexual function, and a big piece of tissue comes out in one piece because it's a malignant tumor. We typically throw that away as medical waste, but as a physician, it's incredibly valuable for teaching radiology, pathology, correlates. And here is Jane and Joe Malachewski, who's a pathologist who's really into this with an RTEC scanner. So the word RTEC scanner and hospital and pathologist usually don't coexist in the same sentence, but because of what we learned at Rapid, it does. And that's a 3D printed osteosarcoma of the sacrum, which is now being used for teaching. So for the mandible, we can take apart things in the maxilla as well, which is harder because sometimes you have to take the eye. If there's a big malignant tumor, sometimes you have to take the eye. I skipped that picture just for you, but you can see these are very large tumors that go into the mouth, go up into the eye, and you have to remove the entire eye. So if you're doing a surgery that's going to defigure someone in the fact that they're going to lose that part of their face, You better be accurate, and you better take it all out and give them the best 5-year chance of survival they can get. We do the same thing, though. There's data. We say, why can't we do that in the maxilla? There's a piece of the fibula. You can use the scapula. You can mirror image the normal to the abnormal side. And then KLS Martin made these plates just for that patient. And those guides are just for that patient and just for his resection. So he'll look as normal as he can. Now, we get these emails and comments sometimes because we're in the hospital. And they say, I've been taking out the mid-face for a long time. I think I'm pretty good at it, you know? And these guys are quick at Mayo to tell you, I don't need that thing. We're doing a really good job. That's just kind of a new shiny squirrel. But they have constantly come back and said, we like it, because their goal is to take somebody like this, remove a large piece of their mandible, and send them out after the swelling stops like this. You could not tell that woman had half her mandible removed unless you saw a little scar underneath her jawline. And that's the goal. Now we can move on to thoracic surgery because we have very pioneering thoracic surgeons. And they came to us and said, we want to be able to take out what's called pancreas tumors through small incisions. And typically we make big incisions like this, where the black lines are, and saw through all those ribs and saw through the shoulder blade, because we need to get to a place where we can see all the stuff. We don't know where all that stuff is, so we have to open them up and loop it off, where all the critical vessels and nerves that go to the arm. And instead of doing this, a week in the hospital, lots of postoperative pain, we want to be able to do it like this. No rib spreading, no rib cutting, looking through small ports. In fact, one of the thoracic surgeons said, you'll never be able to do it. You can't take a pancreas tumor out like that. You'll leave tumor behind, which is a good challenge to one of our thoracic surgeons. That's a big tumor. It's sitting in the apex of the lung. And all the things above it, which you're not going to see if you're coming from below it, is everything you don't want to injure. Blood vessels you don't have control over, all the nervous function to the arm, so the person wakes up and their arm isn't dead on their side, immobile. So the model initially was very helpful, but we didn't know it would be very helpful. And this is why being in the hospital, being in close proximity to have engineers, doctors, radiologists, surgeons, all who talk to each other and are allowed to freely integrate. People walk in our lab, I don't say, what's your PAU number? How are you going to pay for this? We provide a service to the patients at Mayo Clinic. So she came down and said, well, what do you want in the model? That's Shonda Blackman with Jane. And said, well, I want everything in the model. I want the brachial plexus. Now we have to do an MRI. I want the CTA. I want the vessels. I want the tumor. I want the bronchus. And this model was the first pancreas tumor model, which should look like nothing to you. But I can tell you, to the surgeon, this was incredibly impactful. She walked out holding it, rotating it, thinking, I can do this. I have the confidence to know where I am from below to do this. And it was the first one that had ever been done. This is just some of the segmentation work, which is not trivial. You know, to say, well, I want the trachea one color, and I want the tumor one color, and the ribs one color, and the arteries one color, and the brachial plexus from an MRI another color. So now you have MRI and CT and segment. It's like a segmentation nightmare in my book. But why would you do it? Because now she can look up there and take this tumor out in one piece, and that person had no rib cutting except for those 2 ribs next to it, and left the hospital in 3 days. That's different than a week and a ton of postoperative pain and maybe 2 to 3 days in the ICU. Our ICU days are about $3,000 a day. So every day you save, who cares how much that model cost, right? Because you're saving $3,000 an ICU day, and if your OR times come down to $80 to $100 a minute, then you'll capture the money back. And we do quite a bit of pancreas tumors now because it's successful. And also, for the first time, a patient was able to look down at his own anatomy. They don't understand CT or MRI. I don't know if anybody's ever had a CT or MRI. It's difficult to understand. But here they can look down and see what their anatomy is. We do large chest wall resections. There are a lot of big body parts that come out at Mayo Clinic because we see a lot of complex tumors, because it's going to take multiple surgeons working together to do this. It's interesting that the picture on your left, the medical illustrators even like, because they say, I can't get this view. If I'm going to draw this tumor for a publication or for whatever, there's no view like this that exists. So sometimes the medical illustrators will steal the model, draw a little sketch, and then put it back on the table before anybody knows. Everyone at Mayo seems to want to operate in their best possible capacity, which is, I'm from Boston. You know, there's got to be a reason why 3,000 some odd physicians who are kind of at the top of their game live in a cornfield. And it's because you're allowed to work together with people who are all trying to do the same thing. where it's not about you, it's not about me, it's not about that surgeon, it's not about someone's pioneering technique, it's only about the patient. And when you work like that as a physician, then you can say, I can't go work somewhere else that's siloed. Some of these tumors are incredibly vascular, so every one of those purple squiggles, that red one's the biggest vessel in your body coming out of your heart. It pumps 5 liters per minute. You have to move that out of the way and take that green thing out in one piece. And if you nick one of those little purple squiggles, there's going to be about 6 liters of blood in the chest cavity, and you're going to have 4 suctions in there because that's how much it bleeds that fast. So the surgeon came out and said, this was the easiest pancreas tumor I've ever done. And we said, why? And he said, because Tom Foley, who segmented it, was spot on with every one of those squiggles. And all I did was bring the model next to the OR table and put a clip everywhere he told me one of those things were. That's different than going in there blind and trying to find them as you tease your way around, and now it's 11 p.m. and you're still there trying to get this thing out. The surgeon was just gaga about that. You can imagine. They want their life to be somewhat easier too, because that's better for the patient. If they're not in there for 8 hours, that's better than for the patient. The lung surgeons constantly want to take things out smaller and smaller, which means you have to know which blood vessels go into that little part of the lung instead of taking out just half the lung. So there's a little hook that's on a little blood vessel, and they use these models now to say which blood vessel goes to just that tumor, meaning I just want to take just this little segment, which is better for the patient because now their oxygenation is better. In vascular surgery, we used to open people up. Like my grandfather in a AAA repair, you're opened up like that. There's a lot of retractors, and people fix your aorta. The aorta is the big blood vessel that feeds your whole body. Now they do most of it through stents, and the average infrarenal abdominal aorta through a stent is very easily fixed. However, what if you want to do this? What if the entire aorta is damaged? What if you have to do that fast? My mother-in-law passed away in August of that disease. It happens fast when it ruptures, and sometimes you have to do that. This stent did not exist. This technique did not exist. Putting a stent across the blood vessels at the top that go to your brain and then putting other stents into it didn't exist. But we had an incredibly talented vascular surgeon who did a lot of interventional work who said, I think we can do this. But it's different to say, I think we can do this and do it on a patient versus can you guys make us a model? So he was aware of what we could do, and then we had the patient come, which is usually how it goes. This is just another picture of stents and stents. He came in, not looking like this, with chest pain, diaphoretic, short of breath, with a partially ruptured descending aorta, right where the vessels that go to the brain are. And the anesthesiologist said he will not survive the surgery. We can't put him all the way to sleep for the length of time. He won't make it out of here. You have to do it endovascularly. And he said, there's not a stent to do it endovascularly. So there's a clinical need. You'll see this all throughout the talk. That came up, and he had an aorta that looked like this. That outpouching coming at you is a thin-walled aneurysm that's already partially ruptured. The in-hospital mortality is upwards of 70% if you show up with a partially ruptured aorta and you don't deal with it acutely. So he came to our lab and said, the company is going to make me a stent. They can have it here in 2 days, 2 to 3 days, FDA compassionate use. Can you guys make us a model? And you say, I could segment an aorta. I could probably give you a solid aorta, but now you're talking about you want to practice. They're going to make 2 stents, one for the patient, one for the model. And that was on a Thursday. And we had to say, okay, can you have something by Tuesday? And it's Thursday or Monday or Sunday. So the ORs are on the 1st floor of St. Mary's Hospital. This is one of the hospitals at Mayo, and we are on the 6th floor. So surgeons freely walk up and down the floors to say, I have a problem. Just 2 weeks ago, we had a surgeon walk in and said, I've cut half of a pelvis out, and we have a problem. Can you print me a model by tomorrow morning? That's a logistical challenge for some of these printers. But, of course, now that we had a clinical engineer inside the hospital, in our department, she took over.
Mm-hmm. So Dr. Oderich, the vascular surgeon who kind of pioneered these simulation models, came into the lab and drew up this aorta, and then we started labeling, and we kind of got into the engineering mode where we started labeling different diameters of specific lumen. The lumen is just the inside wall. So when we create the aortic model, we want to make sure that the inside wall is perfect and completely representative of the anatomy. But then we can build things on the outside to maintain the integrity of the model when we're pumping heated water through it. So there's various parameters that we had to talk about, and these were things that just kind of came up, and we kept saying, well, how thick do you want it? Well, just make it thick. Well, how thick do you need it? How thick can I make it in a giant block? Well, no, I still want a shape of an aorta. So with Todd's help and Materialize in general, we were able to develop this aortic aneurysm simulation program. And I'm just going to show a little bit of how we do that. We use mimics to segment the anatomy. We're isolating the aorta from the rest of the anatomy so that we can get that lumen. Once we have the lumen, we can move into the computer-aided design phase once we have a three-dimensional object. So this is kind of a standard segmentation technique for radiologists at Mayo Clinic. What's not standard about this is when we go into our CAD program and develop a wall. So we have to smooth out the inside. We want to make sure the inside of the model is smooth. We're going to hollow it. Andy, stop pointing at us.
Yeah. That's why he got the picture.
Sometimes the surgeon will say, I know that this vessel only has a diameter of 3 millimeters, but I would like you to dilate it because when we 3D print the model, it's going to be more rigid than the actual vasculature is in the patient. And they want to make sure that their catheters, the needle that they're threading through, is going to be able to make it through the model. So we'll go through and we'll create a center line. We'll sweep a nice curve along that center line to kind of make a faux vessel, and then we'll add that to the original anatomy. And so we're doing a lot of change, but keeping with the original center line of the lumen of the model. This is just kind of showing how we build it together and how we combine everything into a 3D printed model. The most important part of these models is the lumen. We want to make sure that we've got a nice smooth part that we can then hollow out, cut off the tips, add specific size connectors that are going to work with our pulsatile pump. So these are all design considerations that we have to take into concern when we're working with the surgeon, when we're working with the plumber who hooks up our model to the pulsatile pump. Before we even print, we've got to talk about all of those different parameters. Okay, the final check that we do is we'll pull the model back over onto the imaging and ensure that the lumen is intact, that we haven't altered that lumen in any way. We use a Stratasys Objet 500 Connex 3 to print these aortic models. We used to use Tangle Plus, but now we use Agilus, but a Shore 27 on the inside and outside of the model, and then a rigid core of ViroClear. This is an example of Mr. Hall's case, the aortic representation digitally, the model itself, and then the simulation where they've hooked it up to a pulsatile pump, they've injected contrast, and the surgeon has done the entire surgery, but on the model instead of for the first time on the patient.
And it happened the same day. Procedure on the model, procedure on the patient.
Information about the pump. I know you guys want detail. And then here are just a couple of the different setups that we've had. I think we've printed over 50 aortic aneurysm simulation models. And in the beginning, they weren't as robust as they probably could have been. But it worked the first time, and then it didn't work a bunch of times. And so we had to do a design evolution on this. That's Dave, our X-ray technician and plumber that I keep referencing.
We definitely had an aorta death bin.
Oh, yeah. Graveyard.
Like a delaminated aorta death bin.
Things weren't always very, very functional. We had to kind of go back to the drawing board and think about different ways to design these so that they were sturdier and could withstand the pressures and the volumes that we were putting through. So here are some pictures of world-renowned vascular surgeons who are learning to do the surgery on the stent or on the model. And again, the only variable is the model. Everything is the same. The OR is the same. The surgical team is the same. All of the instrumentation is the same. But they're doing it on a piece of plastic instead of on a human being. This is my favorite picture because they're all just smiling. I love it. They're just so happy that they're able to train and educate their fellows this way.
And nobody's nervous in that picture, right? You're deploying a stent on a model. You're not nervous that this is not going to work. And you're crossing blood vessels that feed the brain, and you could have a life-ending stroke on the table. And you'd say, well, why don't you just do it in a simulator with haptic feedback? That's good, but the surgeons are doing this for the very first time ever. That stent did not exist. And they wanted to see the stent come out, and they needed to have all the logistics because someone's coming through the arm, 12 centimeters of catheter that way. 2 people are coming through the leg, and there's 120 centimeters of catheter that way. There's logistics beyond just making the stent that go into making this happen. The amount of catheter work you have to have in there. And they said, no, we want it all out. And the company was gracious enough to say, okay, we'll bring all the stuff for the model and for the patient. And by doing that, having the company there, the 3D printing people there, the engineers there, the help of Todd late at night sometimes, having everybody together was all for him. That was the focus. The focus wasn't about the technology. It was, how do we get this guy out of the hospital alive without cracking his chest so there's a high mortality? That's the beauty of it. You know, the person that had the worldwide greatest experience of doing anything even remotely like this had only done 10 cases. He was flown in, you know. And then you had chief engineers that were inside the, it's not advancing, inside the room, along with different, oh, there it goes, along with different surgeons that were there. There were cardiac surgeons there to say, if this doesn't work and we occlude a vessel, we're going to have to open his neck and open his carotid up so he gets blood flow to the brain. There were a lot of surgeons in there because the first time you do anything, there's a lot of people in there, one, to make sure everything goes right. And I can tell you everything went right the first time we ever did that. And the average stay is 10 days. That's $1,700 a day for if you open somebody up to do a thoracoabdominal aorta. And you're putting a stent across all the blood vessels that go to the spine. So there's a chance you wake up paralyzed. So I go up to that room basically 2 times a week to put lumbar drains in for these people. And he left the next day after that stent was put in there. He looked so good, he left the next day. And he does not care about 3D printing or any of that stuff. He just assumes I'm at the Mayo Clinic and they're going to do whatever they can to get me out of here alive. And that's what his wife said, that you guys did everything you could for him. And that is incredibly rewarding. That's why you would stay there late at night on the weekend trying to get this thing done. Now you can train other people. So now people come and watch cases that are done live, and they go in the next room and do the exact same case with the exact same material. So you don't have to train people on patients. You can have them watch the case and then train them on the model. In fact, one of the intracranial aneurysm devices had it in their protocol that you had to do 10 models. You had to do 10 devices on models as part of being certified. Now, as Amy said, it wasn't all glorious. Sometimes we hooked it up to the pump and there was water spilling all over the place. So then again, it went back to Amy and we said, we have to redesign something. And we made this iterative design to make thicker walls. She put a circle around acute angles. She put a hard inner core in there. And then we called it the Iron Man. It kind of looked Iron Man-like, maybe just to us. But it certainly didn't leak, which was a huge advantage. And then our physicists took it and did, finite element analysis. Said, is this right? Did the printer work? Is it the same as a CT scan? Is it degrading? So we'll leave vascular and go into orthopedic oncology. The man on your right has been taking out large pieces of pelvises, half a body, since before CT was invented. And he even became a believer in the model. And you say, Frank, why do you like the model? And that's Pete Rose with him. And he said the same thing. There's a lot of things that I get from the model that I couldn't have known until I'm in the surgery. And there's a lot of surgeries that were invented at Mayo Clinic about taking people large pieces of pelvises out, half of a pelvis out. And how do you reconstruct them? How do you put that back together so that this person can be functional and walking? They might not have bowel and bladder incontinence because they have a colostomy. So here's a woman, one of the early models of pelvic surgery there. It was a 38-year-old woman with a pelvic sarcoma, and it was a large tumor. And they said, we're going to take the right leg. So a hemipelvectomy, external, take the right leg from the midline over, and they're going to remove that entire piece. Now the surgeon took this and said, I think after looking at the model, we can save the right leg. I think we can move the hip up into the right leg and save the right leg and do a limb lengthening appearance. And he came back and said it would have never happened without the model. We were in a standard procedure, external hemipelvectomy. So it would have never happened without that model. And now most of the large pelvic tumors at Mayo Clinic go to the OR with models. In fact, we couldn't even do a randomized trial because they wouldn't want to participate, because they're that helpful to tell them where the tumor is, where they can make cuts, where the vessels are, because if you've already taken someone half their body off and they have a recurrence, there's only so much more that you can take of that person. So they want to be very precise. All the tumor, but leave as much as the functional person as possible. Now, in pediatric surgery, this is Chris Moyer, who operates on very small children. And 3D printing is made for this because there aren't a lot of devices for 3D printing in peds. And in adults, it's, there's a lot of common things in adults. In kids, even if it's a common thing in a kid that leads to mortality that's not an accidental injury, it's rare, even if you're an expert. Because even if you're an expert, they say, well, you should be mentored for about 5 years because patients are, there's not a lot of rare cases. And everyone is online rating you at how good you are as a pediatric surgeon, right? And you only may see 3 of these things a year, because if you just do the straight math, and there's 800 members in the American Pediatric Surgical Society, maybe congenital anomalies, you'll see 1 a year, 2 a year, 3 a year. So that's even the expert seeing that low number. So they need stuff for simulation. They're constantly asking us to print things life-size. They do not want it blown up. They want it the size they're going to be working on, because they want to simulate what they're going to do. Like this 12-year-old who has a large chest mass, and the surgeon wanted to take it out from the inside. And he said, can you take the green part off, which is cartilage? I can get that off from the inside, and just show me the rock. And when the rock wasn't touching the vessels, he said, this is the best thing for this child. Now, the rest of the people doing the surgery, they're all outside of there. So he knows where he is. He's looking through a keyhole. It's a tiny little scope. There's a beating heart. There's the tumor. There's about 4 other people in there trying to get trained on how to be a pediatric surgeon, right? And they're holding the model. Where are you? Looking at the model. Maybe they're doing some of the scope work. And then they took the tumor out from the inside, which is a much better morbidity for that patient. And then you'll see his finger poking in. They were saying, I think that's a little tumor. Bring the model over. And they brought the model over, and they looked at the contour and said, yeah, that's not rib, that's tumor. That saves that child from going back to the OR the next day or the next week. So I think they, I keep getting messages to introduce the Vietz family video. I'll show a couple more things here. That in pediatric surgery, they are the most common person to ask us for lifelike stuff. If you could go back 1 slide right to there. If you could go back to that slide at the beginning. Because this is a diaphragmatic hernia, which means all the bowel is in the chest, and they have to train people how to put the bowel down back into the chest. Well, this would be a really hard thing to simulate and teach somebody with plastic, right? With things that aren't very flexible. And those are 2 millimeter size instruments. Those are really small instruments that he does. So he's constantly asking us, can we get more realistic material? Because they're asking us to operate on smaller and smaller. We have a whole team at Mayo that just operates on intrauterine babies. That's as small as it can get, 22 weeks gestation. So they want life-size stuff. And that's really why the model helps, because it could be as big as whatever screen you project the model on. It could be that big. Now, we helped a family, so we're running a little bit late, I think, and they want me to show this video. So maybe you can skip ahead to the 3rd to last slide. Can you do that back there? And then we'll talk about this last case. So if you go to the third to last, yeah. So, these are all patients. While we're experts in 3D printing, and Amy is an expert in biomedical engineering and 3D printing, and we're hiring another engineer, we have segmenters, we're only here because of the patients. If this didn't help patients, we would not be staying late, working on weekends, doing whatever it took to help these patients. And this was a baby that was born with, or it was intrauterine. If you can go back 1 slide from there. It's an intrauterine, so there you see the ultrasound. The baby's in the womb and the heart is beating. The problem is the heart is beating outside of the chest cavity. So that's called pentalogy contrail. It's super rare. There's about a 95% chance that baby dies the second it leaves the womb. So they either abort them or they prep the families for burial, and the baby's going to die, and they use principles of hospice for that. But the family came to us and said, we want to give our baby the best chance it could be. And the surgeons came to us because we work with them on a lot of other things, said, can you make us a model of this baby? We'd say, well, how are we going to do that? We can't make models from ultrasound yet. I mean, you can make some crude models. But they said, we'll get an intrauterine MRI. And we said, great, this is going to be segmentation all day. But we made this model. And there's the model with the hole. And I sat there while 21 other physicians in a room passed this model around, said, what if we took more liver out? What if we took more liver out and put the heart back in? Would that be enough space? Can we get an intrauterine tissue expander? And then pediatric cardiologist said, you don't have to fix that. You don't have to fix this. We know the physiology. Don't worry about that. Worry about getting the heart back in the chest. We'll fix that VSD later. We'll fix that PDA later. And they just all sat there and came up with a plan. You put a stitch in the heart because we don't want the aorta to torque. And it was the greatest thing to watch because there were so many disciplines in that room, part of radiologists, part of 3D printing, yes, but really more doctors, surgeons, cardiologists, pediatric congenital cardiologists coming together to get this baby out of the womb alive. And that baby came out and one person put a stitch in the heart. That's all they did. Kept it from kinking. And another person, Dr. Carl Rose, was there, and they brought that baby out and that baby lived and went home. So those parents brought that baby home. That's a dramatic outcome by a huge team of doctors that came together. And 3D printing played a small role, but it's a tool. It's a tool to enable people to be better than what they are. So there's a video that SME did. They called them up and asked them if we could record a short video with them and see some live views of the baby, and they agreed to it. So we'll watch a small video here. And that'll be the end of our talk, so we really appreciate you coming, taking the time to be here this morning, and doing everything you do within this community to advance it so we can take things from here and bring them right into the clinic. So we'll watch a video now.
Hi, we are Brian, Caitlin, and Kieran Beats. We'd like to take a moment to share our story with you. We found out at our 20-week ultrasound with Kieran that she would be born with her heart outside of her body as part of a condition known as pentalgy of Cantrell. From there, we attended maternal fetal medicine appointments in Fargo, North Dakota, where Justin Horner highly recommended we see cardiovascular surgeon Joseph Durrani at Mayo Clinic in Rochester, Minnesota. So we drove out and met him not long after. Then about, I think a month and a half later, we drove out for more appointments where I had a fetal MRI of Kieran taken. And from those images, we learned that Mayo was going to print a 3D model of Kieran to practice her surgeries before she was born. And we were incredibly excited to be part of something
so new and groundbreaking and just really cutting edge technology.
Around week 35, we drove back out to Rochester for delivery. We had planned on a delivery for March 17th, but with all high-risk pregnancies, sometimes the plan changes. My blood pressure had started to shoot up and Kieran's heart rate was dropping. So Dr. Durrani and everybody pulled together in about an hour and a half to bring Kieran safely into the world. The surgery took about 5 hours, and we got to meet Kieran around 1:30 in the morning, where we noticed the model sitting on her counter in her room.
We walked in and we saw the model off to the corner, and at first we weren't quite sure what it was, and we walked up to it and saw it, and we recognized it, and it was just really cool to see it, and we weren't sure if we were allowed to keep it or not, and we had the nurses ask, and sometime later we finally found out that we get to keep it. It was really great. I mean, most people they get a ultrasound picture of their child, and here we have a little statue of our kid before she was even born.
Yeah, so as far as we know, I think we're the only ones who have something that cool, which it's always a conversation piece to the right audience, of course. Some people find it a little weird, but for the most part, we have people that are just astounded that doctors are using technology to plan stuff like this. Most of what people know about 3D printing technology is
They'll print out little gadgets.
Yeah, that you can get on Amazon
and stuff, or
you know, and
it's really amazing to be a part of this technology that it's still in its infancy and it has so much potential for the whole world. I mean, we're just starting to scratch at the surface on what's possible.
We'd like to thank everybody who was part of the whole experiment, everybody who designed the model and printed it, all the teams at Mayo who made her surgery possible, and she wouldn't be here without this technology. So, I mean, from the bottom of our hearts, we can't thank you guys enough for all the work that you do for the medical field.
Yeah, thank you.
Hey, Kieran, come here.
Come here, Kieran.
Can you say thank you?
Say thank you.
Say thank you.
Say thank you. Bye-bye.
Can you blow a kiss? Go. Mwah. There you go. Say bye-bye.
Bye. Thank you.
Yeah, absolutely.
That's really what it's all about, isn't it? About that patient outcome at the end. Thank you so much, Dr. Morris, Amy Alexander, for being here and presenting such amazing content. I know you'll stick around for a few minutes after if people have questions and they want to talk to you. Great. Absolutely. Fantastic. We have a little thank you for you just for being here today. Thank you so much.
Thank you very much.
Thanks so much.
Really nice
We're going to take a quick photo here. So much. Thanks again to our presenters. Don't go away because we have to announce the winner of this year's Rapid Plus TCT Innovation Award. And we would like to remind you at this point to make sure and vote for another award we're going to do tomorrow, which is the People's Choice. So when you're out on the show floor today, there's a spot in the app to vote for your favorite exhibit. Please do that. So now, without further ado, we would like to announce the winner of the 2018 Rapid Plus TCT Innovation Award. It was very close. It was about 5% different, so make sure you go see both of those exhibits and understand the technology that they're bringing forward. So on behalf of our sponsor of the Innovation Audition, Smith Packer McWhorter has given 10 hours of legal counseling for government contracts or construction-related matters. It's an estimated $4,000 value, and that's going directly to the winner. So when I announce the name please come to the stage. Ladies and gentlemen, this year's Rapid Plus TCT Innovation Award winner is NanoSteel, 3D printable tool steel for powder bed fusion. Jonathan, please come to the stage. Metal Flow and Carl Decker for creating that 3D printed award that we had. So that was great. So every day at Rapid Plus TCT, we're giving away 3 copies of the Wohlers Report. So Terry Wohlers, if you could join me on stage, and we'll do that right now. Okay, Terry, we have to pick some numbers here again. We have a list of all the full conference registrants. So give me a number.
91.
91. Ooh, I'm already in the hundreds. 91 is Nathan Brooks. Nathan Brooks, if you're here, please join us afterward, and we will give you your voucher for the Wohlers Report. One more number.
Yeah,
2 more.
2 more numbers.
Yep.
540.
540. Still turning. Close. So 540 is David Ott with Stryker. So David Ott, you've won a copy of the Wohlers Report.
And, 702.
702. All the way. 702 is Jacob Carlson. So Jacob Carlson, please join us afterwards and we'll be giving you the voucher. Please be sure to come tomorrow morning and hear all about Terry's latest information here at Rapid Plus TCT. Thanks, Terry.
Welcome.
Thank you. So thank you to our presenters and today's keynote sponsor, Materialize. Please join us this evening on the show floor for a networking reception from 5 to 6 p.m. The show is now open. Please join us on the show floor and enjoy all the exhibits. Thank you.